Welcome. This is Dr. Sudha, Associate Professor, Department of Mathematics, Drupatunga University. In this session, let us look into the definitions of conjugate and self-conjugate of a subgroup of a group G, examples, and a few lemmas. To begin with, let us look into the definition of conjugate. If H is a subgroup of a group G, then XH X inverse where X belongs to G is called a conjugate of H. Suppose if H is a subgroup of G and XH X inverse is equal to H for some X belonging to G, then H is called a self-conjugate. If two subgroups A and B of a group G are satisfying A is equal to XB X inverse from X belong to G, then they are said to be conjugate to each other. Let us recapitulate the definition of P-Silo subgroup. Let G be a finite group. A subgroup H of G is such that order of H is equal to P to the power of M, where P is a prime, and P to the power of M divides order of G, and P to the power of M plus 1 does not divide order of G, then H is said to be a P-Silo subgroup of G. Let us discuss example wherein we have the modulo group Z6 with respect to addition modulo 6. We know that order of Z6 is 6 and 6 can be written as 2 into 3 using prime factorization. And we also know that Z6 is cyclic. And here 2 divides order of Z6 and 2 square does not divide order of Z6. So this implies Z6 has a unique 2-Silo subgroup of order 2 using first Silo theorem. Similarly, 3 divides order of Z6 and 3 square does not divide order of Z6. Once again, Z6 has a unique 3-Silo subgroup of order 3. And this is also once again using first Silo theorem. Therefore, the 2-Silo subgroups, that is 2-Silo subgroup and 3-Silo subgroup, both being unique, P-Silo subgroups of Z6 are self-conjugate. And this also follows because Z6 is cyclic. Let us consider the second example, that is Z4. And G is equal to Z4. It contains 4 elements. And let us take a subgroup H, that is 0 and 2. Let us take X is equal to 1. Then X inverse is equal to 3 with respect to addition modulo 4. Let us consider XH X inverse. So this is a set containing the elements wherein we obtain after operating X from the left side and X inverse from the right side with respect to addition modulo H with respect to H. So X is 1 and X inverse is 3 and H is 0, 2. So 1 addition modulo 4, 0 addition modulo 4, 3, the first element. Second element is 1 addition modulo 4, 2 addition modulo 3 is the second element. When we operate this, we are going to get 4 and 4 under addition modulo 4 is 0. And when we operate this, we are going to get 6 and 6 under addition modulo 4 is 2. So we get the set containing 0, 2 and that is H itself. So X, H, X inverse is equal to H for X is equal to 1. Therefore, H is self-conjugate subgroup of G which is equal to Z4. Let us discuss the first lemma here. Let A be a subgroup of G. Then we need to prove that order of A is equal to order of X, A, X inverse. That is conjugate of A for all X belonging to G, where X, A, X inverse is equal to X, A, X inverse, where A is a element of subgroup A and X is an element of group G. To show that these two subgroups have same order, we are going to define a mapping phi from A to XA X inverse by phi of small a is equal to X A X inverse where X belongs to G. First of all, let us show that phi is a well-defined mapping. That is, if we take any two elements are equal, that is A1 is equal to A2, we can operate x from left side and x inverse from right side, and we get x A1 x inverse is equal to x A2 x inverse. By the definition of phi, x A1 x inverse is phi of A1 and x A2 x inverse is phi of A2. Therefore, phi is well defined. Now, next, let us show that phi is 1, 1. Let us assume that the two images are equal. That is, phi of A is equal to phi of B. We need to show that A is equal to B. By the definition of phi, we can write this as xa x inverse is equal to xb x inverse. Since xa and b are all elements of G, using the cancellation laws in group G, we can cancel x on left hand side using the left cancellation law and x inverse on the right hand side using the right cancellation law, and we get A is equal to B. Therefore, phi is 1, 1. Now to prove that it is onto, let us take an element y in the codomain, that is x a x inverse. Since y belongs to x a x inverse, y can be written as x small a into x inverse, where a belongs to a and x belongs to G. So for an y in the codomain, we have found an a in the domain such that phi of a is equal to x a x inverse, and that is y. Therefore, phi is onto. Since phi is 1, 1 and onto, phi is bijective. Since phi is a bijective mapping, the order of, that is the coordinality of the domain set is equal to the coordinality of the codomain. Therefore, order of A is equal to order of xa, x inverse, hence the lemma. In the second lemma, we need to prove that if A and B are subgroups of G, then order of AXB, that is the double coset AXB, is equal to order of AXBX inverse. Now let us define a mapping once again from phi to the double coset AXB to AXBX inverse. So let us consider an element of AXB, that is phi of AXB is equal to AXBX inverse. Now let us show that this mapping is well defined. Let us take two elements equal. A1x B1 is equal to A2x B2. Now let us operate with x inverse from the right side. Since x is an element of G, its inverse exists, so we can operate from the right side and obtain A1x B1 x inverse is equal to A2x B2 x inverse. But from the definition of phi, this element is phi of A1x B1 and the element on the right hand side is phi of A2x B2. Therefore, phi is well defined. Now let us prove that phi is 1, 1. Let us take the images of two elements are equal. That is phi of A1x B1 is equal to phi of A2x B2. So by the definition of phi, this is equal to A1x B1 x inverse is equal to A2x B2 x inverse. Now by using the right cancellation law, we can cancel out x inverse from the right side and we will obtain A1x B1 is equal to A2x B2. Hence the images equal implies the elements are equal. Therefore, phi is 1, 1. Now to prove that phi is onto, let us take an element in the codomain, that is AXB x inverse. That is small a x, small b x inverse, where A belongs to A, B belongs to B, and x belongs to G. This implies AXB belongs to AXB, the double coset, such that phi of AXB is equal to AXB x inverse. Therefore, phi is onto. Since phi being 1, 1 and onto, it is a bijective mapping. Since it is bijective, order of domain is equal to order of codomain. Hence the lemma. Now let us discuss the third lemma. Show that order of AXB is equal to order of A into order of B divided by order of A intersection XB x inverse. Here we are going to make use of one of the identity in the set theory, that is order of AB, that is the product sets, is equal to order of A into order of B divided by order of A intersection B. Here we are going to consider the left-hand side, that is order of AXB, but AXB is equal to AXB x inverse using the second lemma. Now we can treat this as two sets here. One is A, the other set is XB x inverse, and we can make use of the above identity of set theory and write down this as order of A into order of XB x inverse divided by order of A intersection XB x inverse. But order of XB x inverse from lemma 1 will be equal to order of B. Hence the lemma. Thank you.